This is my AP research presentation on HHO injection and internal combustion engines. So starting off, what is electrolysis? So electrolysis is the utilization of electricity to split water into hydrogen and oxygen gas. Current is passed through the water, usually using metal plates. The process of electrolysis produces HHO, which is hydrogen and oxygen gas. The aim of this study looks to improve the fuel efficiency in internal combustion engines. This can have implications to any engine that runs on gasoline. Being more fuel efficient would mean that the engine produces less emissions and consumes less gas. This means increased fuel range and spending less money at the pump. Some terms to know for this presentation include RPMs, which stands for the rotations per minute, which is the measure of how fast the engine is spinning or running. It is measured by a tachometer and measures how fast the crankshaft is rotating per minute. HHO, this is water, H2O, that is split into its separate elements of hydrogen and oxygen in the form of a gas. MPG stands for miles per gallon, and this is a measure of how fuel efficient an engine is. An HHO generator is usually a configuration of metal plates that act as electrodes to carry out the process of electrolysis. Different setups can produce gas at different rates and power efficiencies. Moving on to my literature, I collected 12 articles and split them into 3 themes based on the content of the study. The first theme was diesel-specific fuel consumption. This theme included studies that carried out their research by running an engine on a specific amount of diesel each test with and without the addition of the injection of HHO to find if there was a difference in the amount of time it took for the engine to consume all of the diesel it was given. These studies demonstrated an increase in the engine's runtime with the injection of HHO. This indicates that HHO injection increases fuel efficiency. This is because of the engine's ability to run for an extended period of time. My research will be focused on the specific fuel consumption topic as well, but focused on using gasoline as the fuel source instead of diesel. The second theme that I found from my reading was studies that looked at emissions and power differences between running an engine off of only gasoline and gasoline with the injection of HHO. These studies looked at the differences that HHO injection made to emissions as well as brake power and brake torque, which are separate tests that measure the different proportions of engine power. Brake torque and brake power are shown to increase with the injection of HHO. This increase is due to HHO's high flammability and flame speed. On the emissions side, almost all emissions tested were decreased. It has been found that HHO injection decreases carbon monoxide emissions, increases carbon dioxide emissions, and sometimes increases nitrogen oxide emissions. While carbon dioxide increase sounds alarming at first, it is important to look at the whole picture. With the injection of HHO, a complete burn occurs in every combustion cycle. This means that all the gas injected into the engine is combusted and none of it is wasted. In turn, this results in a higher carbon dioxide emissions, but also higher brake power, increased brake torque, and improved fuel economy. The third theme is gas-specific fuel consumption in HHO dry cell configurations. This theme included 2 studies, with one really standing out. These studies stood out from the others as they displayed the configurations of the HHO generator setups along with concentrations and liters per minute. This is different from other studies because it goes into depth about specific HHO generator setups along with their output of HHO. These studies found that as surface area and concentration level increases, HHO production increases as well. This is because as electrical resistance goes down, HHO production increases. With lower resistance, more current can flow through the generator, and with higher current, there is accelerated electron movement between the electrodes of the generator. This results in an increase in HHO production. These studies go over surface area, electrode material, and gap distance between the plates of the generator. They also include information about specific fuel consumption, suggesting an increase in the consumption of in a fuel efficiency improvement. My research study used a review of a comparative study on the effect of hydroxyl gas in internal combustion engines on engine performance and exhaust emissions, primarily as a mentor study to how this study was set up. My gap in literature included the HF16S, which is a generator that I custom built for this study. This generator combines the natures of both a wet cell generator and a dry cell generator. And along with tracking the surface area, concentration mixture, concentration and electrolyte mixture, liters per minute. I will also be tracking efficiency values, which I find that studies fail to describe. My other gap is testing the specific fuel consumption on an XT675 49cc Kohler engine, which has not been used in research. So this leads to my research question. How does the HF16S affect the specific fuel consumption of an XT675 49cc 4-stroke Kohler engine? And my hypothesis is that with the injection of HHO, specific fuel consumption will be improved for the XT675 49cc Kohler engine. Moving on into my methodology, my independent variables were my electrolyte mixture and my amps supplied. My amps supplied were kept the same throughout the entire experiment at 45 amps. The electrolyte mixture was kept the same for that specific test, and the processes to make that electrolyte mixture were kept the same throughout the whole experiment. My dependent variables were the volts the generator pulled and the amount of HHO the generator produced. These depended on the electrolyte and concentration mixture. My other dependent variables were the RPMs that the engine ran at and the consumption of fuel of the engine. The engine RPMs depended on the rate of consumption of fuel and also the injection of HHO. Fuel consumption depends on how fast the engine is spinning or the engine RPMs, which is influenced by the injection of HHO. And my control group was, for experiment 2, was running the engine off of just gasoline. This was my non-injection group. This is an overview of my experimental research. So for my first experiment, I tested which concentration and electrolyte mixture made the generator produce the most HHO gas. And for my second experiment, which engine testing, I ran 5 tests for my control group, and I ran another 5 tests for the HHO injection group to compare the differences with and without the injection of HHO. So diving into my first experiment, or generator testing, I tested how much HHO gas the generator was producing at that specific electrolyte and concentration level to determine which electrolyte and concentration level would be used in the second experiment, or engine testing. I also recorded how much energy the generator was using, which is how many volts the generator was pulling. A test was completed by starting a timer and turning on the generator concurrently, and measuring the amount of time it took for the generator to produce enough gas to displace all the water in the 21 fluid ounce bottle being used to collect the gas. I conducted 3 tests for each specific electrolyte and concentration. For example, I tested sodium hydroxide at a 10% concentration level and ran 3 tests on this electrolyte. My generator holds 1,650 milliliters of water, and this means that 5% is about 83 grams. 83 grams of electrolyte is added for every 5% increment. This data is then logged into a spreadsheet. Moving on into my experiment 2, or engine testing. For engine testing, I tested whether HHO injection had an effect on the runtime and RPMs of the engine. I did this by running 5 control tests where I filled the engine with 2 ounces of gas for each test and timed how long the engine ran on this amount. I used a tachometer to read the RPMs of the engine and logged every RPM that the tachometer measured into a spreadsheet to later calculate average RPMs in miles per gallon. I then ran 5 more tests completing the same procedure, with the only difference being having an HHO injection system set up to inject HHO into the engine. This is a picture of my HHO injection system. So on the left is the engine, and on the right is the carburetor, and in between is the HHO injection system. Without the injection system, there's a black spacer in between. Moving on to my findings for experiment 1. This is time versus concentration, with the vertical axis being time in seconds to the time in seconds the generator took to displace all the water of the 21 fluid ounce bottle with HHO, and on the horizontal axis is concentration in a percentage. Sodium hydroxide in blue and potassium hydroxide in yellow performed at about the same rate, while baking soda in red outperformed the other electrolytes, producing gas at a faster rate. Moving on to my discussion of experiment 1. This graph is a liters per minute versus efficiency percentage. So on the vertical axis is the efficiency percentage, and on the horizontal axis is the liters per minute of HHO gas produced. On the far right, you can see baking soda producing at a higher liters per minute than all the other electrolytes, and on the far right, producing at 0.86 liters per minute and almost 69% power efficiency is my 10% baking soda concentration in an electrolyte mixture. That baking soda 10% concentration in electrolyte mixture was then used in experiment 2. And moving on to my findings of experiment 2, this is my this graph shows average RPM and time. Average RPM is on the vertical axis, and on the horizontal axis is time in minutes. In green is my control group or my non-injection group, and in red is my HHO injection group. For the injection group, you can see a downward trend that as time increases, RPMs decreases. And this is because if the engine is spinning faster, you're consuming more gas, which means that the engine is going to run out of fuel in a quicker, at a faster rate. So that's why we see this downward trend. However, for HHO injection, we don't see this downward trend, which is interesting to see. Moving into my discussion for experiment 2, this graph shows miles per gallon versus time. So miles per gallon is on the vertical axis and time in minutes is on the horizontal axis. My miles per gallon for the HHO injection were consistently higher than that of the control group. And this agrees with my research done for my literature review, that specific fuel consumption is improved. There is also higher RPM with miles per gallon was also higher as well because of the engine running at a higher RPM with the injection of HHO. Moving into my conclusion, my experiment 1 showed evidence that baking soda at a 10% concentration is the most effective electrolyte mixture. This is because it had the highest liters per minute out of all the other electrolyte and concentration mixtures. It was also the most power efficient concentration in electrolyte mixture, producing HHO gas at almost 69% efficiency, higher than all the other electrolyte mixtures. The results from experiment 2 showed that HHO injection extends specific fuel consumption. This proves my hypothesis right, as it makes the engine more fuel efficient. This was seen in the increase in miles per gallon seen in experiment 2. My results supported the results of the studies I curated that specific fuel consumption is improved with the injection of HHO. Limitations of my study include that the tachometer that I used to measure RPMs of the engine. The tachometer is supposed to read values at every one second interval, but didn't quite read values at this interval. However, the same tachometer was used in every test, and I feel like it recorded enough values to cancel out any error that might be associated with this. Time was controlled by humans, but I feel like there is enough data that supports the conclusion that the results are accurate enough to draw a confident conclusion from the study, especially with a t-test value that shows a significant difference with a t-test value of p equals 0.0114. This means that there's a 1.14% chance that with the injection of HHO, the improved miles per gallon happened randomly. Well, since this value is less than 0.05, which is the 95% confidence interval, then it is concluded that these results show a statistically significant difference between the miles per gallon test of the control and injection groups. Since since RPMs also changed significantly, but time did not, we can interpret this that the miles per gallon improvement came from better combustion or reduced waste, not just a slower burn of the fuel. Implications of this research include many facets. The HHO generator used in this study is a completely new design that reached high levels of power efficiency. Further prototyping and refinement of this generator design can lead to further improvements and possible breakthroughs in the electrolysis world. On the HHO injection side, these results have implications that can be applicable to any gas-consuming internal combustion engine. This research supports the idea that with the injection of HHO into any gasoline internal combustion engine, there will be an increase in fuel efficiency. This probably has the widest reach as an application in vehicles. This is something that can be implemented in vehicles to improve fuel efficiency, meaning improved emissions, longer fuel range, and money saved at the gas station. And then these are my references.
Questions? You ready?
Yeah.
Can you you talk to us about how do the choices you made when designing or implementing your research method impact your research process?
So they impacted my research process because I chose to do experimental research. So I decided to do experimental research because I thought that it would be best applicable to the project that I was thinking about doing. And in doing so, I also decided to do tests, a certain type of testing that I went deep into detail with. So I have lots of data that I logged into my spreadsheets and can draw suggestions from this data.
Okay, thanks.
I'm interested to hear, how does your new understanding address a gap in the scholarly conversation?
So this addresses a gap in the HHO generator world, electrolysis world, as I address the gap that the articles I curated in my literature review failed to state is the power efficiency of the HHO generators. So I focused a lot of my time on figuring out how to document the power efficiency of the HHO generator. And along with this, I also tested the specific fuel consumption of an engine that I haven't seen tested in the research that I read.
Brennan, and for a final one, I know you had a lot of fits and starts as you worked through the research process. So if you could start this project over again, what's the one major change you would make to your process?
I think I would make my process more streamlined in the way that I conducted it. So I now know like background of what I'm doing. When I first came into this, I didn't really know what to expect or what to do. But now I feel like I can streamline my process a lot more with my HHO generator testing. I can condense what I did there a little bit, and then I feel like in my engine testing, I definitely like to see different engines tested.
Terrific, thanks so much for that. Ash, you all ready?
Yeah.